SwayamPrabha. Digital India. Educated India. SwayamPrabha. Digital India. Educated India.
Let us have a look at cost optimization of commuter and regional aircraft. These kind of aircrafts belong to a very specific category of transport aircraft, and therefore it is very important to understand what are the issues involved in operating them in an optimized fashion, and also the various costs which are related to their operation. The outline of today's lecture is as follows. We will start with a discussion about commuter and regional aircraft, explaining what they stand for and what is so special about them, what are their features. We will then move on to a discussion on the concept of generalized cost, specifically the generalized cost of travel. From there, we will then focus on only the generalized cost of air travel. Next, we will describe a specific routine which has been developed for analysis of commuter and regional aircraft operations, costing and sizing. One important part of this particular routine is the cost estimation model for setting up and operating a small regional airport suitable for commuter and regional aircraft. So, we will look into the details of that particular model, and in the end we will present some case studies on the application of this particular model for three contemporary commuter and regional aircraft. So, what are these aircraft? These are aircraft which are used in air transportation for short haul travel. By short haul travel in air transportation, we mean flight over distances of approximately 1000 kilometers or 500 nautical miles, because 1 nautical mile is 1.853, nearly 2 kilometers, and also these aircraft generally carry lesser than 100 passengers. There are no hard and fast definitions, these are just the industry norms. If you look at the literature about such aircraft, what I mean is aircraft used for short haul routes, you will find that almost all of them, with only a few exceptions, have two engines which are mounted on the wings, one on each wing, and these engines for the commuter aircraft tend to be turboprop type, and for the regional aircraft they could be turboprop or turbofan engines. Two prominent examples of commuter and regional aircraft are as follows. The first one is a commuter aircraft. This is the Dornier DO 228 aircraft. the one that you are seeing is DO228NG. As you will notice, this aircraft has only about 7 to 8 windows, 3 here, 4 here and 1 here. So, basically it has around 19 seats, and you can see it has got a high wing with 2, in this case they are turboprop engines. Another example of a regional aircraft is this ATR 72-600, which again has a high wing configuration or a wing mounted over the fuselage. It also has 2 turboprop engines, and in this case there is a vertical tail which is of a T type configuration, or if you look from the rear it looks like T. These are 2 very popular and very successful aircraft in the commuter and regional category respectively. ATR 72 can handle approximately 66 to 72 passengers, and DO228, as I mentioned, carries between 15 to 19 passengers. There is a version called as DO228-100 which carries 15 passengers, and there is a version called DO228-200 which used to carry 19 passengers. The NG is a new generation version of DO228. These aircrafts are characterized by high cost per seat per unit distance. This is because the total cost of operating this aircraft is shared by lesser number of passengers compared to the airliners which have maybe 180, 200 or even 300 passengers. So, there the costs are shared over a large number of passengers. So, the per kilometer per passenger cost comes down, but commuter and regional aircraft suffer from high seat mile costs, and therefore, the airfares on these routes or on the routes that these aircraft offer tend to be higher per seat per kilometer compared to those for the airliners. But such aircraft, by virtue of their ability to operate from small airports, ability to carry less number of passengers, they are excellent for testing the markets or looking at new markets, untried markets. These are very good aircraft to operate, because even though the cost per seat per mile may be high, but the total overall operating cost is low. A very important consideration about these aircraft is that in their case, not only is the configuration of the aircraft important. By configuration I mean the location of the wing, the type of wing aerofoil, layout between the wing and the tail, etc. That is the design aspect or the configuration aspect. So, that is important, but not enough. Even the flight profile that you follow or the trajectory of the aircraft when it goes from A to B, even that is also very important. It has been shown in studies that if you look at a trajectory between 2 cities located or 2 airports located less than 1000 kilometers, if you look at the optimum trajectory from the point of view of only fuel consumption, the best trajectory will probably be what is called as a sawtooth trajectory, in which you take off from the origin airport and slowly climb to an altitude from where, if you descend slowly, you will hit the destination airport, which means there is a complete absence of cruise in case of only the least fuel consumption profile. So, that is why the flight configuration and flight profile both are equally important. In the case of airliners or long range transport aircraft, medium range and long range aircraft, what you will find is an aircraft climbs to a cruising altitude and then spends substantial time cruising at that altitude. In many cases, when we have a long distance cruise, the aircraft actually undergoes 1, 2 or even 3 changes in the cruising altitude. As the fuel is consumed, the aircraft becomes lighter, and as the aircraft becomes lighter, the optimum altitude required to cruise while maintaining the cruise Mach number is higher than what was before, because the aircraft is lighter, you require lower lift to manage the weight. Weight has reduced because of the consumption of fuel, therefore, you require lower lift. So, if you want to maintain the speed, not compromising on the speed, then you have to have flight at a lower density than in the previous case, and that means it is better for you to climb up. So, the cruising altitude can change from 35,000 to 38,000 to 41,000 during the 10, 12, 15 hour flight of a long range aircraft. So, the time and the distance which is covered in the climb and the descent segment can be completely ignored in case of airliners, but not so in the case of commuter and regional, because it is quite possible that the time spent in the climb and the descent phase and the distance on the ground travelled in that phase will be comparable or even sometimes more than the distance spent in the cruise. So, therefore, it is a very interesting case study in aircraft design, where you got to look at not only the configuration, but also at the flight profile. Another very important point when we talk about commuter and regional aircraft is the very stiff competition that other modes of travel such as the rail or the bus or even the personal automobile. These alternative mode of transport actually provide a huge challenge to the air transportation, because the operating costs by air transportation mode can be much higher and the distances are much shorter. So, over those distances a passenger might find it more convenient and affordable to travel by alternative modes of transportation. In case of medium or long distance travel, air transportation perhaps becomes the only practical mode of travel. For example, if there is a flight from Mumbai to New York, do you think a passenger would even consider going by automobile or bus or by a train on such a long route? Probably if a person is interested in spending time, they can go for a cruise. There are many people who take a cruise which will take probably 3 weeks or a month to travel from here to New York, stopping at various destinations, but that is different. In those cases, travel is not the main purpose. So, when you come to short range travel, when you look at, for example, a travel between say a city like Mumbai or to a city like Pune, then personal automobile or railway or bus service or taxi service can become very competitive as compared to an air travel, because when you travel by air, you need to first start from your origin, go to the airport. You need to report sufficiently early so that you can do the security clearance. So, you might have to report a couple of hours before the flight or maybe an hour before the flight, but at least 45 minutes before the flight, because the gates will close around half an hour before the departure, and then you have to do before that you have to undergo security and check in. Similarly, at the destination you need to spend some time to pick up your baggage. If you do not have any check-in baggage, if you have only the carry-on baggage, still from the destination you will have to again take a mode of transport to go to your final destination. In such a case, the total time spent, the total money spent becomes far more as compared to rail or bus. but there is no such problem when we look at medium and long range transportation. So, these are some of the interesting features and the challenges in planning air transportation using commuter and regional aircraft. So, therefore, we will look at one such attempt to model their design and their operation. To understand the concept of generalized cost of travel, we need to appreciate that travel actually consists not just the travel by one mode, but by many other modes which are required before and after the journey. So, the generalized cost of travel essentially stands for the total effective cost that a person incurs in undertaking travel. So, there are direct components of the travel cost which are consisting of the fare that is paid by the passenger for various segments. And then there are certain indirect cost components. For example, to undertake travel from origin A to destination D, one has to spend time, and this time comes with its own cost. Then some infrastructure has to be made available enabling this travel to take place. For instance, if you have to travel by your own car from O to D, then there has to be a motorable road. If you are travelling by train, then someone has to invest in the railway line infrastructure and the construction of the railway stations and also provision of the railway services. Similarly, all modes of transportation do not have the same level of comfort associated with it, okay. Especially when you have to change the mode of transport many times, it can be considered to be the one that gives some discomfort to the passengers. Now, some passengers, they may not worry about the discomfort because they may think that they are saving money or time, so they do not mind a bit of discomfort, but for some passengers this discomfort may be a larger component of the cost. For example, if there is a disabled person or an elderly person who has difficulties, they would prefer if possible for a short range travel to just get into a car and get off at the destination and maybe stop in between wherever they want if they want to take a short break for whatever reason. They would not like to undergo the trouble of hopping on, hopping off, hopping on, hopping off through various modes of transportations. The overall cost may be much lower if you hop on and hop off. For example, you may say I will first walk to the bus stop, take a bus to the metro station, then take a metro to one more point, then from there I will take a bus and go to the other city, again I will get down and take walk some distance, take a bus, again I will take a metro, again. Some people do not mind this because for them the total cost and the time saved is important, as compared to some elderly person who would say I do not mind paying more money, but I want to just get in and then keep sitting in the car. It may take more time, it may face traffic congestion, I do not care, but I am concerned about the discomfort. So, there is a money value associated to the time spent in travel, there is a money value associated to the discomfort that you are able to withstand, and there is also a money value associated in setting up and creating and maintaining the infrastructure that is required for the transportation to take place. So, these are the indirect costs of travel. So, time cost, as I mentioned, depending on how much is the value of time of a passenger, the more time you spend in travel, the higher will be the time cost. So, the value of time is a function of the income of the passenger. Okay. People who have higher income levels may be more sensitive about the time spent in travel. They would prefer, even if it is a bit more expensive, they would prefer to go by a mode that takes less time. Then it also depends upon travel type. Is it a travel on personal visit or is it a travel on official visit? Is it happening in the middle of the night or at a very inconvenient time, or is it happening at a convenient time. So, all these factors decide how much is the value you assign to the same unit of time. So, 1 hour of travel time may actually have a connotation of 2 times compared to daytime travel compared to a nighttime travel, or weekend travel compared to a weekday travel. Then by all modes of transportation which have a particular frequency and a particular timetable, a person has to adjust their travel based on the availability and the timetable of the transportation system. Whereas, if you have your own automobile or your own vehicle, then the moment you want to travel, literally at that point you can start your travel. You do not have to advance or delay your travel because you have to match with the timetable. If you are flying from Mumbai to Pune, for example, you will have to align your travel with the frequency of the aircraft and the timings of the flights which are available at the airport. So, let us say you get a call to come to Pune at 10 o'clock in the morning, but the next flight is available only at 3 o'clock in the afternoon. Then you will have to delay your travel by 5 hours, because you cannot take a flight, it is not there. In these 5 hours you might actually reach Pune by your own mode of transportation. So, defer time is very important. Depending on the frequency and the availability of the mode of transportation, defer time is low or high. Generally, when you have higher frequency, you have lower defer time. When you have lower frequency, you have higher defer time. There are some airports which do not operate a daily flight. For example, recently I went from Mumbai to Kolhapur, and from Kolhapur I came back to Mumbai. Now, the flight available today is only, there are flights only 3 days in a week. So, I had to adjust my schedule, keeping in mind that look, I can't come back on this particular date because there is no flight. So, I had to stay 1 day extra. So, I had to defer my journey by a day, and if that particular time was very important for me and I wanted to do something else during that time, I could not do it. So, there will be some time cost associated with deferring my journey. And as I mentioned, infrastructure cost is a very important component of generalized cost of travel, because to enable the transportation system to offer you the possibility of travel, someone has to set up the infrastructure, and also it has to be maintained and kept working. If you look at now air travel, in air travel again there are some direct costs and then there are some indirect costs. The main direct cost in air travel is the flight cost or the airfare that you pay as a passenger. This airfare has also many components. You are paying for many things. You are paying for the operating cost of the airline. You are also paying for certain taxes, certain charges, maybe navigation charge, maybe landing charge, maybe passenger handling charges. All that can be clubbed as taxes or airport charges, and the airline has to charge some profit to stay in business. So, all of this put together constitutes the fare which you pay, which is the direct component of the generalized cost of air travel. Okay. And the operating costs, as we all know, we have seen it already, are consisting of the direct operating costs which are connected with the flight operations of the aircraft or the airline, and IOC is the indirect operating costs, which are costs associated with the business aspect of the airline. The airport charges, as I said, is consisting of landing fee, pax handling charges, and also other charges. Then, to reach the airport from your origin, you need to take some mode of transportation to access the airport, and also when you reach the destination, from the airport and the destination you have to go to the eventual destination. So, you need to take another mode of transportation, that is the access cost. Usually it will be the taxi fare that you pay to travel from your starting point to the airport and from the airport to the destination. time cost. It will be the time spent in the flight, time spent in accessing and time spent in the deferring of your journey or preponing of your journey to match with the schedules. The fourth component is the infrastructure cost, which has been termed in this particular analysis as airport cost, and this will consist of costs associated in setting up and operating an airport to enable flight operations to take place. So, in short, the generalized cost of air travel is a combination of four major terms: the flight cost, the access cost, the time cost and the airport cost. In case of short haul air travel, each of these components could become a bottleneck. We do not know which one. Okay. It is not that just the flight cost is the highest, sometimes the time cost because of deferred time can be a big problem. So, to handle all these complications and the features of commuter and regional aircraft, a routine was developed to estimate the generalized cost, which is called as CRAGER. CRAGER stands for Commuter and Regional Aircraft Generalized Cost Estimation Routine. So, this particular program or procedure can be used for carrying out the synthesis and the trajectory optimization of a commuter or regional aircraft in a unified fashion, because as I mentioned, in such aircraft it is not only important what you fly, but also how you fly. So, the what part comes from the synthesis or from the configuration, and how part comes from the trajectory or the mission profile that you follow. This tool is designed to analyze multi-stage missions of such aircraft. Let us have a look at what is meant by a multi-stage mission profile. So, this is a classical single stage mission profile in which an aircraft takes off from airport A, goes to a climbing altitude, travels a long time in the cruise segment and then comes in and lands in the destination. This is a single stage mission profile. Compare this with a multi-stage mission profile. Here we have shown 4 segments. Here you take off from a starting point and you land at some other point, and then you again take off, go to some distance and land again take off, go and land, and finally you may come back to the same destination or you may stop at some other destination. So, this multiple segment. Now, in between these 2 segments there may or may not be time or the facility to refuel your aircraft. So, many a times a multi-stage mission is flown with enough fuel right in the first segment to take care of all the 4 missions, assuming that you will not get the facility at the intermediate airports to do the refueling. So, this is called as a multi-stage mission. CRAGER can handle multiple stage missions by bringing in a very interesting and a unique feature which I will talk about. Since it is a routine for commuter and regional aircraft, and since it does synthesis, it has modules for various tasks which are done in aircraft design, and I will show you the flow chart very soon. Many of all these procedures, they had to be validated. So, for that data related to around 4 dozen existing aircraft of this category, commuter and regional, right from 15 seaters to about 80 seaters, all the data was collected, collated, and several trends were then generated based on the data, and many of these trends were used in the calculation procedure. It has, apart from the module for access cost and the flight cost, it also has the modules for airport cost and the time cost modules. These are the 2 unique modules in the CRAGER routine. The routine consists of a total of 20 design variables. Design variables are variables whose values are changed or modified within a specified upper and lower bound to try and obtain an optimum solution. So, 11 of these variables are related to what, that is the aircraft configuration, and 9 of these variables are related to how or the flight profile or trajectory related parameters. We will discuss about these 20 variables very soon in the next slide. Also, because it is an optimization routine, it generally should have some constraints within which the objective function has to be optimized. In this case, the objective function is the generalized cost of travel, and the aim is to minimize the generalized cost of travel. So, the idea is to arrive at values of the 11 configuration related variables and the 9 trajectory related variables, which minimize generalized cost of travel while meeting these 10 constraints. 4 of these constraints are related to the aircraft operation, and these are equality constraints, and 6 of these constraints are derived parameters which are given as an inequality constraint. Many of them are pseudo constraints just to ensure the feasibility of the design, and a few others are specific constraints, as we will see in the next slide. Now, another interesting aspect of Kraiger routine is that to handle the constraints, it uses what is called as a penalty function approach. So, what we do in this approach is that if a combination of certain design variables corresponds to an infeasible case because it violates, let us say, 2 of these 10 constraints, then what we do is, in direct reference to how much is the constraint violation or in proportion to the constraint violation, we add a penalty to the objective function, and because we are minimizing, this additional penalty is going to inform the optimization routine that this direction or this particular combination is not a good direction to go, because the objective function is turning out to be higher. So, in a cost minimization routine, if we say that there is a constraint on some parameter which is not being met and therefore you add an additional cost, it is a way of informing the optimizer that you have to look for a better solution. So, we will now look at the complete list of variables and we will try to explain them one by one. First, we look at the 11 configuration related variables. The first of these is wing area. Now, wing area is something that has to be properly defined. In aircraft operations or in aircraft sizing, the wing area is the area of the wings of an aircraft in the platform or in the top view, including the part which is inside the fuselage, as shown in this particular cartoon. Okay. So, that is the definition of wing area. It is not just the area of the 2 wings, but the area of the 2 wings plus the area of the portion within the fuselage, flat area within the fuselage, which is the projected area. The next parameter is wing aspect ratio. Wing aspect ratio is an indication of the slenderness of the aircraft. Okay. So, if an aircraft is short and stubby, then the wingspan, which is the distance from one wingtip to the other, will be less. For a given amount of area, when you have lesser wingspan, you have lower aspect ratio, because aspect ratio, which is normally shortened as AR, is equal to square of the wingspan divided by the wing reference area. So, as you can see, for a given area, if the wingspan is increased 2 times, the aspect ratio is increased 4 times. Also, for a given wingspan, if the area is reduced, aspect ratio increases. If the area is increased, aspect ratio reduces. The next parameter is wing taper ratio. Wing taper ratio is measured as the ratio between the chord of the aircraft at the tip divided by chord of the aircraft at the root, which is inside the fuselage. So, you extend the leading edge and the trailing edge of the wing for it to meet at some point on the fuselage center line, and the root chord at that point is generally going to be equal to or higher than the root chord at the tips generally. So, Ct upon Cr, okay, normally called as lambda, that is the taper ratio, Ct upon Cr. Usually you will find that the value of lambda is either 1 or less than 1. Typical values are approximately between 0.4 to 0.45 or 0.5. The next parameter is wing thickness ratio. So, this is, if you look at the cross section of the wing, you will get an aerofoil cross section, and the thickness is actually the distance between the lower and the upper point on the aerofoil, and there is one location marked here by C at which the thickness is maximum, the numerical value is B, and the total length of the chord of this aerofoil is A. So, B upon A, that means the maximum value of the distance between the lower and the upper surface, perpendicular distance of the chord of the aerofoil, wherever it is maximum, that value divided by the total length is called as the wing thickness ratio, normally called as T by C, because T is thickness and C is the chord. And then we have wing leading edge location, which is, if you have an aircraft, here we have taken two aircraft, one which has got some kind of a sweep and the other which has got no sweep. So, location x from the nose to the place where the wing starts on the fuselage or where the wing is located on the fuselage, that distance divided by the length either L1 or L2, that ratio x upon L1 or x upon L2, that ratio is the wing leading edge location. So, yes, it varies between 0 and 1 theoretically, but you never have wing mounted right in the front or right in the back. So, generally the value of this parameter varies from something like 0.25, 0.3 to about 0.6, 0.7. So, you will notice that the configuration of the aircraft is strongly dependent upon these parameters of the wing. Hence, we have taken 5 of these parameters. The next one is the rear fuselage length. Now, this is the side view of a typical commuter aircraft fuselage. In this case, we have taken the silhouette of Dornier 228. So, you can have the fuselage into 3 parts, the front part from the nose to maybe where the passenger cabin starts, the middle portion which is the passenger cabin where people sit, and then the rear portion. In the top view, it looks like this. So, this particular length is the rear fuselage length, and one may even parameterize it in terms of the ratio of this length upon total length. Then the next parameter is takeoff flap deflection. When an aircraft takes off and lands, it needs flap to be deflected to provide camber so that the lift coefficient is increased to help in maintaining a short distance required for takeoff. One can have various types of flaps and one can have various angles of deflection. If you have a simple flap with lesser deflection, then its cost, complexity and weight is lower. If you have a much larger deflection with a very articulated type of flap, let us say slotted flap with Fowler arrangement or multiple slots, that will be much more expensive, much more complicated. The next variable in Kraiger is maximum takeoff mass. Now, interestingly, maximum takeoff mass is actually an output and not an input. In most aircraft design procedures, you actually estimate the maximum takeoff mass. But in the case of Kraiger, we have specified maximum takeoff mass as one of the design variables for a very special and very interesting reason, which I will elaborate when we come to the constraints. Similarly, the ninth variable, design variable in Kraiger regarding the configuration is the total fuel mass. This also is something that actually gets calculated. You fix a configuration of the aircraft and then you fly the aircraft from starting point to the destination through various segments. You actually estimate the fuel consumed in each segment, you add them together and you get total fuel mass. But in Kraiger, we have given total fuel mass also as one of the design variables. Maximum takeoff power, this is a parameter that decides the size of the engine and also to some extent the fuel consumption and also the weight of the aircraft. And finally, the last parameter related to the configuration of the aircraft in Kraiger is the balanced field length. Suffice it to say that balanced field length essentially can be considered as the total pavement that is required to be available for safe operation of the aircraft from a particular airport. So, the balanced field length is a kind of a surrogate for the runway that has to be constructed. Larger balanced field length will correspond to more runway length to be constructed and hence higher cost of runway construction. A smaller balanced field length would mean a lesser runway length to be constructed and therefore lesser expenses in the construction of the airport. Coming now to the trajectory or the profile related parameters, there are as you know there are 9 of them. The first one is the climb throttle. As I mentioned in the preamble, the commuter and regional aircraft are a very interesting subcategory of transport aircraft, where not only what you fly, but how you fly is important. This is one of the hows. At what engine setting do you climb? Do you have a very steep or sharp climb, or do you have a very shallow or low angle of climb? So, this depends on how much is the throttle being provided during the climb phase of the aircraft. Similarly, when you come into descent, you have to bring the aircraft down from the cruising altitude to the location where you are landing. Now, if you do not exercise any control, the aircraft can literally fall like a stone and come at a very high speed. This particular phenomena of extremely quick rate of change of the descent can cause a problem with the passengers' comfort. So, generally aircraft come in at a fixed rate, and if the aircraft is pressurized, then one does not bother much because the pressurization system can take care of the problems. But in case of commuter and regional aircraft, because they fly at short distances, we do not want to go to high altitude. As I mentioned to you, cruising altitude is not really very important or even very high in the case of such aircraft, because there is no benefit in climbing so high. You may as well climb to a height of 15,000 feet, 20,000 feet and then come back and land. So, therefore, these aircraft are generally unpressurized, and when they are unpressurized, it is very, very important to ensure that the rate of descent is something that is manageable by the human body. For that, the throttle that is used during the initial descent phase and the final descent phase, it has to be controlled within some upper and lower limits, which are the two variables in the Kraiger. And then at what speed do you climb? Again, this also makes a big difference. What is the Mach number at which you cruise? Then what is the speed at which you descend? At what altitude do you cruise? And also, because it can take care of multi-stage missions, one has to have a method of estimating the fuel consumed in each of the stages. Now, as the aircraft becomes lighter, even if you travel the same distance, you will consume lesser amount of fuel because you are lighter. So, assume a case where you go from A to B, B to C, C to D, D to E, and all of these are equidistant. And if you carry the entire fuel in the first segment itself, because there is no refueling facility available, or there is no time available to refuel because you want to do it quickly, you want to hop multiple times, then in that case what will happen is that the fuel consumed in the first segment will be much higher than that in the last segment, because the aircraft is much lighter in the last segment compared to the first segment. To take care of this particular estimation, in Kraiger we have something called as a cruise fraction of the main stage, which is the fraction of the distance which is travelled in cruise upon the total distance travelled. As I mentioned to you, this fraction may be very small or even absent, it may be even 0 in case of a commuter aircraft. So, what we do is we try to find out how much of the mission distance or trip distance should be covered in cruise, remaining portion in the other two segments of climb and descent, and this we calculate for the main stage and for one more stage which is called as the notional stage. This notional stage is a kind of a surrogate or a replacement for the remaining multiple stages. It is assumed in Kraiger that the fuel consumed in the notional stage will be constant for all the other stages. It is an assumption, but it makes the life very easy. So, with these 20 variables 11 plus 9, let us now have a look at the constraints in Kraiger. There are two types of constraints. The first one is related to the operation of the aircraft. Every aircraft needs to have a certain climb gradient or certain ability in maintaining a particular climb rate from safety point of view, and WAT stands for weight, altitude and temperature limited. So, these three parameters, weight, altitude and temperature, they actually impose huge constraints in the climb gradient. So, at the design gross weight, at the specific altitude and specific ambient temperature, you should have 2.4%. The climb gradient would be the excess thrust available upon the total thrust produced, T minus D upon T. Then we need to ensure that we do not command from the engine more power than what is required by the aircraft to maintain the cruise altitude at the cruise speed and the cruise Mach number. So, for that there is a constraint that the main cruise throttle should not be more than 100%. Because the aircraft is unpressurized, we put a constraint that the maximum rate of descent will be 500 feet per minute. This number comes from industry practice and from a survey of literature on what is the kind of rate that is being followed by contemporary unpressurized transport aircraft. And then aircraft tend to be very noisy and they create disturbance to the environments. So, there are certain regulations. One of them is the sideline noise level. So, we have looked at 94 effective perceived noise level at around 450 meters from the center line. This is a indication of how noisy the aircraft is. So, the aircraft is considered to be feasible only if the sideline noise is maintained below the 94 EPN dB limit. Then there are some derived parameters. Remember, we had some parameters in the design variables which were actually not supposed to be there, they were supposed to be actually calculated. So, what we do is we use the power of optimization in meeting certain constraints by ensuring that some derived parameters meet the requirement of the actual. So, for instance, there is a very important consideration for transport aircraft from the safety point of view, and that is the static margin. Both from the comfort as well as from the safety point of view, we want to ensure that the static margin of this aircraft is never below 5%. Normally aircraft come with around 10%, 15%. We have given a slight leeway. This number is changeable. It is a number that you put in the code, and then if you want to calculate for higher value, you can always put that value. We had assumed the max takeoff mass as a parameter in Kraiger. So, that is a value, and once you have the configuration and the profile, you will be calculating the fuel consumed in each stage, and therefore, you will come to know what is the actual calculated max takeoff weight. So, we put a constraint, an equality constraint, saying that whatever you calculate should be equal to whatever you have assumed. In other words, the optimizer is forced to assume the max takeoff mass in such a way that after calculations it becomes exactly matching with the value that is calculated for that particular mission. The same thing goes for the fuel mass and also for the addition of the distance travelled in all the segments. So, the main stage length will consist of segments of climb, cruise and descent. Each of these segments will entail some distance to be travelled by the aircraft depending on its parameters. But at the end of the code, the addition of the distance travelled in climb, cruise and descent for the main stage should exactly match with the main stage length, and similarly that distance travelled during the climb, cruise and descent segment of the notional stage length, which is, as I mentioned, a surrogate for the multi element mission. So, you will take one of them as an average and assume that same thing is following. There also we want to be meeting the constraints that whatever you assumed is matching with whatever comes out. So, these equality constraints apart from the static margin, those other ones, they are actually pseudo constraints. They are only there for us to make the code work properly. So, here is the flow chart of Kraiger code. You start and read design variables for the first time, and if you are having the first call, then you read design constants also, because they do not change. Variables do change, but these do not change, and then you carry out the geometry and the sizing. Then you look at the mass estimation, look at the CG and balance calculation, and then you do the aerodynamics, for which you get the propeller characteristics from here, you get the flap data from here, and with the flap information and the prop information, since you already have the aircraft information, you can do the aerodynamic analysis and predict CL, CM, etc. Then you go to mission analysis. There you need power plant data also and the propeller data also, and there are some stage performance numbers which are required. Those numbers come from the code. Finally, you do mission analysis, and then you can do the cost estimation. When you have the cost estimation of the aircraft, you can do the generalized cost estimation. This estimation will require flight cost, airport cost, time cost. The excess cost is considered a constant number in this study. There is no optimization done on location of the airport near or far away, and therefore, the changes in the land prices. We just assume that there is a constant taxi fare that you pay for origin and for destination. So, that is why the excess cost is not included here. Then, using the airfield performance calculations, noise level calculations, and also the costs from various segments, you calculate the objective function, which is the generalized cost of travel, and then you ask a question, is it minimum? Then you stop. If not, you invoke the optimizer. Optimizer will change design variables and send it back here. Okay. Just check that this is the first call or not. If it is not, then you do not go this way, because they are already in the memory, and then you keep on continuing this till you reach convergence. Now, as I mentioned, one of the important components of this particular Kraiger tool is the regional airport cost estimation model. So, let us look at this in more detail today. So, the purpose of bringing in the regional airport cost estimation model is to look at air transportation from the systems engineering approach. What we want to do is we want to have a direct coupling between the aircraft that you are designing and the minimum airport it needs for operation, so that you do not end up spending too much money. Of course, when you make a new airport at a destination, you do not design it only for one aircraft or one possible operation or one airline, you design it for many multiple airlines which might operate, and also you have to keep a margin for the future. But instead of having just one generic airport for every aircraft, we thought better to couple the size of the airport with the size of the aircraft and the way in which it is operated, so that a one-to-one coupling can be obtained between the aircraft and the airport. This is one of the major contributions of this particular work. The idea is that build, own, operate, or build, own, operate and then transfer. These are two approaches for new airport development which are being followed worldwide. This allows the government to avoid massive investment in the infrastructure, whereas one can partner with the government and take help from a private entity to fund the development of the new airport. But when you ask someone to fund the new airport, they are very concerned about how much is the upfront investment needed, can we minimize that, and can we leave sufficient margin in the airport to grow in the future, whereas do not necessarily invest much upfront. So, the question arises, what is the minimum facility, minimum area, minimum land parcel that is required to set up a new airport for operating a particular aircraft with a particular frequency? That was the question which this particular model answers. So, what it does is it estimates the airport cost or the airport infrastructure cost, right, to meet a given demand for air travel or cargo, and a function of the geometrical details and the frequency of a given aircraft, and it is limited only to twin turboprop, commuter and regional aircraft. So, if you want to estimate what is the cost associated with setting up an airport which can handle a particular class or particular types of aircraft of this category, this model can give you that answer, provided you plug in the correct values of some of the constants. This module has some sub modules. The first sub module is the airport configuration module, which using the regulations works out the layout of the airport with a single runway and in the orientation that it should be made. Then it does the airport layout, it does the geometrical design of the airfield, location of taxiways, location of runways, aprons. To do this, we classified the airport under 3 levels: level A, level B, level C, or level 1, level 2, level 3. Level 1 being the most basic simple airport which will handle only one flight a day of one aircraft, and that too only during daytime, okay, and so on and so forth. For each level of the airport, for each corresponding aircraft, we came up with the estimation of setting up cost and the operating cost. Let us have a look at the airport layout. As you know, airport layout is decided based on certain regulations. The FAA uses approach category and airplane design group, which are a function of the approach speed and the wingspan respectively. The ICAO uses an aerodrome control code number and a code letter. The code number is a function of the reference feed length and code letter a function of the wingspan and wheel track. And based on the code number, code letter or category and design group, you can pick up the standard manuals of airport design or aerodrome design, and you can get the runway, taxiway and apron, how many are needed and the dimensions and separation. This model is limited to only single runway airport, okay. But taxiways and aprons, how many are needed, that can be decided based on certain input parameters, as I will show you. So, this is how we classified the airport into 3 levels. Okay. The need of this one is to calculate taxiways their numbers and aprons and their numbers. We need this information to size the passenger building, because as the level will increase, the aircraft will become larger and larger, and there is also a possibility of simultaneous operation of two flights or simultaneous arrival and departure, I mean with some gap. The passengers will be all together in the terminal. What is the minimum equipment of the aeronautical facilities that have to be provided from safety point of view? The basis for this particular classification was to look at the extent of flight operations and to look at the database of existing Indian airports which come under the regional airports in that particular year. So, based on the study of the database, we found that the minimum fit or the minimum requirement in an airport for it to be operating peacefully is to have a non-directional beacon, to have a control tower and one VHF radio. Notice no manpower is being recommended. It is an automated system where there will be a control tower with VHF radio and there will be a facility for receiving messages. And the payment will be flexible, it will not be rigid. So, the basis is operational hours, climatic conditions and the demand for travel. Then this is the minimum equipment. The study limits itself to only flexible pavements with NDB and VHF radio with a control tower. And after that one can keep on adding more and more features. For example, you can add more equipment, like you could add lightings if you want to operate evening operations, or you could add more aprons and taxiways to avoid conflict. So, here friends is the generic airport layout, and as you can see there is a color scheme used here. So, everything that you see in black color is the minimum requirement for a level 1 airport, which will be this one runway and the RPZ in both the sides in the of the runway, one taxiway, one apron, one car park, one terminal building and some staff housing and accommodation, because it is likely that this is going to be away from a city. Then this area consists mainly of the landside area from here downwards. So, in the landside area you need to provide terminal building and a car park and staff housing and accommodation. Level 2 airport is shown in blue color. It includes everything that level 1 has plus some additional items. Notice that level 1 airport has only a black colored radio box with a person. The person is actually in blue color, so we do not need a person, we have just a black colored box. Level 2 has one person here and another instrument. Level 3 has another person also, and in level 3 we look at operations during evening and bad weather and night time. So, you have to put these red colored runway lights. The red colors here shows lighting system which has to be put. The color will not be red, they will have their own scheme, but it is shown in the red here. Aerodrome beacon is required as a unit in level 2 airport, NDB in level 1 airport minimum requirement, and windsock is also there in level 1 airport. This slide shows the geometry of the runway. So, you have the main runway pavement shown in the black color. This is also called as a structural pavement. This is constructed as per some norms. Then you have shoulder on the sides. These are for protection against any injury because of the blast, etc. Because when the engine exhaust comes out at very high speeds, that jet exhaust can create lot of problems. So, that is why we have this blast pad. And finally, the dimensions of the runway, zone width can be obtained by a simple formula. So, using the regulations of ICAO and FAA, one can work out the minimum permissible distance between say the apron and the terminal building to car park, all these minimum values, far side distance, all these numbers, runway width, they are available from those regulations for particular aircraft type. Now, let us come to the airport cost estimation procedure. As I said, there are setting up costs which will have requirement of land area, plus you have to construct airside. For construction of the airside, you need to know the runway length, and for that you need to know how much is the pavement thickness. In the land side, there is a PAX terminal building, and there are some equipments for navigation, plus at every airport you need to set up some kind of a fire and rescue service. At every airport you must set up some fire and rescue service, and the amount of facilities that you have to provide comes from some regulations based on the ICAO category. And then we have the operating costs. So, this will consist of cost towards providing salaries to the staff members, the consumables, and the maintenance of various aspects of the airport and the runway to ensure that operations do continue. So, let us have a look at case study in which we compare 3 aircraft and we actually calculate the airport related costs of the 3 aircraft. One of them is Dornier 228-200, the other is the Saab 340B. This is the medium capacity 35-36 passengers twin turboprop aircraft, and this is ATR 72-500. So, we will calculate for these 3. So, if you look at level 1 airport which is suitable for Dornier 228, you notice that this particular level 1 airport, it is assumed, the one on the top is assumption. It is assumed that the capacity is 19 passengers, which is true, and there is only one flight per day, and if there are 19 passengers, at the max you need 50 people to be handled in the terminal building. So, an airport that can handle DO 228 is categorized as code letter B and reference code 3. So, we just simply calculated for a classic case that the runway length will be 800 meters, width 23 meters, airport width, airport length, area in acres, and the pavement thickness. When we did the calculations for Saab 340B, for level 2 airport, there are 2 flights a day, and one of them could be clashing with each other. Each flight is 35 seats only, and they are in the same code letter B. So, here what we see is that the runway width becomes 30 meters from 23 meters. Okay, that is because of the level of the airport. See, the code category is 3 here, category becomes 4 here. When category becomes 4, there is a minimum 30 meters runway length required, and hence the area of the airport goes from 9.2 to 1.920. The runway length, airport length goes from 920 meters to 1410 meters, and you can see that the area increases from 117 acres to 187 acres. And ATR 72 type 3, this type 3 is not connected to the aircraft, it is connected to the way in which the aircraft is operated. So, here apparently because you are paying more fare, you are going to get complimentary terminal transportation as well as road transportation. So, you can see the airport area is now double, more than double. Okay. The width remains the same. Let us look at the costing of the airport. Okay. This is a fairly detailed old study. So, the costs are in lakh rupees in 1996. Numbers do not matter actually, what matters is the scale up. Okay. So, we see that when we have DO 228 type aircraft level 1 airport, These are the costs associated with setting up various facilities. So, about 513 lakh rupees will be required to set up this airport, and this is the estimation of the annual expenditure. Let us move on to category 2 airport for Saab 340B. The cost is almost doubled, and this one is 1.5 times. And 8702 is category 3 airport, which is the highest you can think of these aircraft, with a night landing facility also. So, there it is almost 3 times the baseline, and operating cost is more than twice compared to a level 1 airport. Thank you for your attention.